Welcome back. Today we're talking about how to do 3D printing using Mathematica. We've already talked about dealing with our functions of multiple variables and increasing the resolution of plot-like functions. Now we're going to talk about meshes and um, what I would say is that this is the internal data structure that Mathematica uses to convert from a perfect object to an imperfect object. So what I would say is, so let's think about something that we're used to. We're used to taking an ideal object and making it imperfect, but maybe more human usable. Consider, for example, the square root of 5 plus the square root of 3. Now this is a perfect number, right? It's a number and it's exactly what we mean. But it would take me some time before I really kind of understood what this number is in decimal value. And so we have a way to take this ideal number and give me this number 2.59, and that really gives me a different way and sometimes a better way to understand what this number really means. Uh, Similarly, you're probably used to having you can think about a heptagon here, so a polygon with 7 sides. And this object, this is a representation of the perfect object that has 7 sides, a regular 7gon. But when you visualize it on the screen, there's a certain number of pixels that are used to show you the object, and if you want to capture it and you want to share this object, then often what you'll do is you'll create an image that is imperfect. And so that can be considered rasterizing an object. And so what we're doing is we're taking this object and we're replacing it by a black and white image that has pixels in it. And I guess this isn't black and white, there's also some gray pixels in it. But this is a 50 by 50 array of pixels of color that represents this object, but it's no longer the same object. This is the ideal object, and this is the object in a way that can be transmitted from one person to another much more easily than saying, here is my 7gon. And well, if you want to do a better job, you can increase the number of pixels that are allowed. But once you've fixed your object to have a certain number of pixels, we can't get back our perfect object anymore. All right, so when we're talking about doing that for a 3-dimensional object, then we use this method called discretization, also called a triangulation of an object. And so what it does is it replaces the object itself, this maybe smooth object or whatever object you have, and it replaces it by a discrete object made up of cells. And so when you hear the word cell, you should think 0-dimensional points, 1-dimensional line segments, 2-dimensional triangles, 3-dimensional tetrahedra. You can even go to higher dimensions, a 4-dimensional simplex, a 5th-dimensional simplex. These objects, any dimension, we can call these simplices. So in Mathematica, there's 2 different ways that these objects are handled, one of which is by the solid cells that make it up, or by its boundary cells. So let's take an example. Let's say we have a circle, and we'd like to represent our circle in a discrete way, right? So a circle is perfect. A circle has no edges, right? I mean, I guess it has 2 sides, right? It has the inside and the outside, but Unlike a 7-gon, it doesn't have 7 sides. There's no number of sides that a circle has. And so if we're trying to represent it by line segments and triangles and points, so by simplices, then we need to make some decisions about how many points we're going to choose around the outside. And we can either represent this circle as a bunch of triangles that have been put together. And so this disk is made up of a whole bunch of triangles that fit together, approximate the circle. Or we can talk about the boundary of this circle, and we can just use a whole bunch of line segments, maybe make an 100-gon, and say that 100-gon is approximately this circle. And so this is the cell representation of the circle, and this is the boundary representation of the circle. Similarly, so what I would say is, because the boundary representation is 1 dimension lower, then it's much easier to work with. However, not every object has a way to represent it in a boundary way. So sometimes you're stuck dealing with this cell representation of your object. And we'll see that that sometimes leads to problems when you're trying to get Mathematica to do something. So if it works, use the boundary representation. If it doesn't work, go work with the discretized, the cell representation of the object. So similarly, we can do this with a ball. So if we had a sphere, a solid sphere, and we wanted to see and break it down, and we can either use a cell representation of it or a boundary representation of it. Now, you can't see the difference here, right? The cells of the ball are a bunch of tetrahedra. The cells of the boundary of this ball is the exterior. So they should look exactly the same. But let's actually, just like up here, we saw these as triangles, and we saw these as boundary line segments. Let's now ask, hey, what are the cells in this cell representation? And if we do that, we can actually access what those tetrahedra are that make up this ball. And I've taken 5 of them, and there they are. There's 5 of them inside the ball. And so, wait, how many are there? This is a good question. I don't know the answer. So, length at this, how many are there? There's 9,197 total tetrahedra in this ball, at least in this way of breaking it down. That number is just an artifact of how Mathematica chose to set up the ball. On the other hand, if we're talking about what are the primitives for the boundary representation, now the boundary representation, so up here the boundary representation of the circle were these line segments. Here the boundary of the ball are the triangles on the outside. And so if we take a number of these, here they are lying on the outside, and so the ball is represented by lying inside the set of all these triangles that are on the boundary. So when you want to create these objects, then you should use discretized region or boundary discretized region if you want the boundary representation. If you have a shape that's a graphics object, use discretized graphics or boundary discretized graphics to get the boundary representation or the cell representation. Okay, so a couple of notes about this. Mathematica developers, they've been making a lot of progress on improving the quality of the meshes and what functions they apply to. When you use export, I think what Mathematica is doing is it's trying its best to discretize each piece of the model and then combining them together. Now, you may be, so what I might suggest is that instead of using export directly, you first discretize your object. So what did we have before? We had our zigzag tube, and we first discretize the object, and then when you export and you import it, we haven't lost those spherical regions because we already helped Mathematica remember that it had to discretize everything along the way. So instead of just using export, you may want to first discretize your object, or discretize each bit of your object, put them all together, and then export them. Let me also talk about improving the quality of your discretized region. So we're talking about taking a ball and breaking it down so that it would have flat sides, right? A ball doesn't have flat sides, a ball is round, and so if we want to represent it by a bunch of triangles and line segments and points, then we have to make a decision about how many of those points we want. One way that we can tell Mathematica that we want there to be more points, so here we have fewer points, and here we have more points. One way to tell Mathematica that we want this to be a smoother object is to tell it that when you're discretizing the object, I want the cells to have to be a certain size and to be no bigger than 0.01. And here we're making this say we want the cells to be no bigger than 0.001. And here we want the cells to be no bigger than 0.0001. And so by changing the size of those cells, we now have a smoother and smoother region. We can do that again for our zigzag. So this was our default value, gave us this zigzag. And if we wanted it to be smoother, so that we could 3D print it and make it just a much nicer model, we can tell it we want a different max cell measure. And now this is a smoother model that we can 3D print and feel that it is smooth around. All right, I'm going to stop here for now, and I'll be right back.